Now we will be discussing about the interference by a thin film, and the shape of the thin film will be a wedge shaped. So that is the interference by a wedge shaped film. So here I have two glass plates, and between the two glass plates I have placed a wire of diameter d. This is a very exaggerated figure. The wire is not this big. The wire will be very thin. So there will only be a very small gap between these two glasses. So this is just an exaggerated figure so that we can look at the diagram very closely. So just think about this. Once one point or one end of the glasses are meeting each other, but the other end is not. So obviously there will be some kind of fluid that is filling this space. It can be air or it can be some other fluid. And what do you think the shape of this fluid will be? The shape of the fluid will be the shape of a wedge. And if air is the medium that is filled in this volume, then we can say that this wedge is an air wedge. So this can also be called as the interference by an air wedge. So let's go to the apparatus. Here we are deriving parallel rays of a monochromatic source, and monochromatic is nothing but it is a single frequency or single wavelength or a single colored source. And how can we derive a parallel rays? That is very simple, just by placing a convex lens and by placing the source at its focus, the rays coming out of the lens will be parallel rays, because the rays passing to the focus after refraction will go parallel to the principal axis. And then we are placing a glass plate so that we can make these rays fall perpendicularly on this arrangement, and part of this will be reflected from the top surface and part of these rays will be reflected from the bottom surface. So we derive two set of rays from the same source. So they will be coherent sources. And what next? If they are coherent sources, they can interfere somewhere. And in order to check how they interfere, we are placing a traveling microscope so that we can observe the interference pattern that is happening over here. So it is the same air wedge that I have drawn below. I have just drawn the geometry of the air wedge here. Suppose the angle between these two glass plates is theta, and this theta will usually be very small, and the diameter is d. Let us take the length from one end to the wire to be L. Now going on to the discussion of the air wedge, let us consider one of the rays which is falling onto the air wedge. Suppose it is happening over here, just like how I have drawn it. At this particular point, the thickness of the film is T. So if you consider this air wedge, one of the ray will be reflected from the top part of the air wedge and one of the ray will be reflected from the bottom part of the air wedge, and these two rays are going to interfere. So in order to understand how they interfere, what all things should we know? We should know the path difference, which we have already derived in our previous discussion about thin films. And what was that expression? That expression was, if there is a path difference, then the path difference delta x will be 2 mu t cos r. This is nothing but the cosine law. We derived the cosine law in our last discussion. This delta x is the path difference, mu is the refractive index of the material or the medium that is present inside the wedge, t is the thickness of the film, and r is the angle of refraction. But in our last class discussion, we introduced an additional lambda by 2 path difference. Do you remember why? That path change was happening due to reflection. And is such a kind of a path change happening over here? Let's look at that. When thinking about the light ray that is reflected from the top surface, there won't be any phase change or there won't be any path difference, additional path difference, because that reflection is happening at a rarer medium, because inside it is air, and here it is glass. So this is reflection at a rarer medium. But if you look at the bottom surface, like over here, it is the initial medium is air and the reflecting medium is a denser medium. So on getting reflected from the bottom surface, a phase change of 180 degree will take place, or we can say that a path difference of lambda by 2 will be introduced in addition to this delta x. So how can we balance that? We just have to balance that lambda by 2 path difference along with the usual path difference. This is the whole catch of the air wedge. Now, what else can we do? We now have the equation for delta x. Now, if you substitute the path difference condition for constructive, then you will get the condition for constructive over here. If you substitute the path difference value for destructive, you will get the condition for destructive indifference over here. But before going into that, let us make some small arrangements or small relationships in this equation so that this becomes practically more feasible, or working out this equation becomes practically more feasible. Because practically finding out this thickness or the which part of the thickness, because this thickness keeps on changing as we go from one end of the wedge to the other end, the thickness is keeping on changing. So measuring the thickness of the air film, because this theta is very small, bear it in mind. So at each and every point finding out this thickness is very hard. That is why I have drawn a distance here which is marked as x. So at whatever position, so maybe just here we are getting a bright spot because of the constructive path difference. Just near that maybe we will get a destructive spot, and just after that we will again get a constructive spot. We will see how that happens. So at each and every time, instead of measuring the thickness, we can just measure this distance x, or the position of that particular fringe. So the only thing we have to do is that just place the crosswire of the microscope first at this point and just move it to wherever position you need, and you will get the value of x. So if we convert this equation in terms of x, it will be more practically feasible. And how can we do that? If you consider this small triangle, can you say what tan theta is? Tan theta is opposite side by adjacent side, that is t by x. So we have t equal to x tan theta. So I can replace t with this. So it is 2 mu, instead of t I can write x tan theta cos r plus lambda by 2. And what is this term? This term is the path difference. And here, as you can see, we are considering normal incidence of the incident light. And what about that? In order for considerable refraction to happen, that usually happens during oblique incidence, or when light ray comes in at an angle. But here we are having a normal incidence or orthogonal incidence, so that this cos r will approximately be equal to 1, because here r can be limited to 0. So cos 0 will be 1. So this value will be 1. So I can rewrite this equation like 2 mu x tan theta plus lambda by 2 will be equal to delta x. Now our derivation is over. Now just we have what we have to do is that just substitute the value of delta x to find the corresponding equations for constructive as well as destructive interference. So for constructive interference, let's look at constructive interference. For constructive interference, what should be the value of delta x? Delta x should be n lambda. So I can rewrite this equation like 2 mu x tan theta plus lambda by 2 equal to, instead of delta x I can write n lambda. So that will be the condition for constructive interference. Again 2 mu x tan theta equal to n lambda minus lambda by 2, bringing this over to the other side. This will be n minus half into lambda. This is the condition for constructive interference. Or we can even say that at x equal to n minus half lambda by 2 mu x tan theta, and whenever x satisfies this condition, at those values of x, or we can say that at those positions of x, we will get a constructive interference or a bright band at these x positions. And what about destructive? For destructive, 2 mu x tan theta plus lambda by 2 should be equal to, what should be the value of delta x? N plus half into lambda. This we have already derived. So then rearranging 2 mu x tan theta equal to n plus half lambda minus lambda by 2, that will be n lambda. You can just derive that, and from this you can write x should be equal to n lambda by 2 mu x tan theta. So at whenever x satisfies this condition, we'll get a destructive or a dark band. So these are the two phenomena or two types of interferences which is happening in the wedge shaped films. So can you imagine anything from seeing these two equations? So let us consider when n equal to 1, at 1 and this term lambda by 2 mu x tan theta, at that value of x we will get a dark point. And where will be the next dark point? When n equal to 2. Then what at so at 1 lambda by 2 mu x tan theta and 2 lambda by 2 mu x tan theta and 3 lambda by 2 mu x tan theta, at all these x values or at all these x positions we will be getting dark points. Then what about at 1.5 lambda by 2 mu x tan theta, at 2.5 lambda by 2 mu x tan theta? Those are these conditions, because just give the value of 1 minus half, that is 0.5. So at 1 lambda by 2 mu x tan theta you will get a dark point. At 1.5 lambda by 2 mu x tan theta you will get a bright point. Again at 2 lambda by 2 mu x tan theta you will get a dark point. At 2.5 lambda by 2 mu x tan theta you will get a bright point. So whenever this phenomenon happens, we will get a series of dark and bright fringes, something like this. And whenever we see a fringe or whenever we see a fringe pattern, the first thing that goes in our mind should be to find the fringe width. Even in Young's double slit experiment, we found out the fringe width of the pattern, because if we know the fringe width, then with that equation we can work out many other things. When we practically do this, when we do this experimentally with the help of fringe width, you can calculate many other useful things. So how can you calculate the fringe width? So if I take this dark point, or if I take the position of this particular dark band, so let that be, what was the condition for darkness? The position of x should be n lambda by 2 mu x tan theta. So x should be equal to n lambda by 2 mu tan theta. Sorry, or did I made a mistake? Here there will be no x, just 2 mu tan theta. So when we bring it to this side, x will not be there, just 2 mu tan theta. Okay. So x will not be there, just 2 mu tan theta. So at n lambda by 2 mu tan theta, we'll get a dark point. So let us just call the x value of the nth fringe. And what will be the number of this dark fringe? It will be the n plus 1th fringe. And so what will be the position of the n plus 1th fringe? It will be n plus 1 into lambda by 2 mu tan theta. And if you just subtract these two x values, so from somewhere we are getting an x value, and from the same position we are getting the next x value, and this is xn and this is xn plus 1. So in order to find the fringe width, you just have to subtract these two distances. So beta will be nothing but xn plus 1 minus xn. And substituting these values, n plus 1 lambda by 2 mu tan theta minus n lambda by 2 mu tan theta. Lambda by 2 mu tan theta will be common in the bracket, n plus 1 minus n, and it will be 1. So you can write this expression like lambda by 2 mu tan theta. This will be the value of fringe width. So you can even rewrite this equation like beta equal to lambda by, if the medium is air, mu value will be 1. So 2 into, instead of tan theta, you can write theta simply. Because we already told that theta is very small. So tan theta will be approximately equal to theta. So this is a very simple expression for beta value. But practically, when we are doing the same thing practically, this is not what we do. Because practically measuring the x values of two adjacent fringes is very hard, because this is an enlarged figure. In actual practice, these fringes are very closely spaced. So finding out the positions of adjacent fringes is very hard while using a traveling microscope. So what we do is that, just like this, we will take the position of the first fringe, that is n lambda by 2 mu tan theta, and then we will take the position of a fringe after a number of fringes, say n plus mth fringe. So after the nth fringe, we will count m number of bands and take some other fringe, and here the equation will be n plus m lambda by 2 mu tan theta. So what should we do? I have these two positions, xn plus m and xn, and when we subtract these distance, will we get the width of a fringe? No, because we have to divide the number of fringes which we counted, and this will be the value of beta. And what will be beta? This value minus this value, we will get m lambda by 2 mu tan theta, m lambda by 2 mu tan theta, the whole by m. Again the equation we will get will be lambda by 2 mu tan theta, which is the same as this, which can be even written like lambda by 2, mu value will be 1 for an air wedge, and tan theta is approximately equal to theta. This is what we do practically. Theoretically this is enough, two adjacent fringes, but practically measuring the positions, x values of two adjacent fringes will be very hard. So this is what we practically do. So why did we measure this? Is there any application for that? Yes, because if you look at this figure, this theta can be related to this d. And what is this d? This d is the diameter of the thin wire which we placed between the two glass plates. So just by utilizing this equation, we can find out the diameter of the thin wire which we used to make this air wedge. How can you relate the d with theta from this triangle? From this big triangle, tan theta is d by this whole length L. So you can substitute this tan theta to this equation. So beta will be lambda by 2 mu, and tan theta is nothing but d by L, goes to the numerator. And if it is an air wedge, mu will be 1, so lambda L by 2d. If instead of air wedge, if it is some other medium, just substitute the value of refractive index of that particular medium. So can we do this experimentally? Yes, we can, because this fringe will be observable from the traveling microscope, and from the traveling microscope you can measure the beta value. The source of light, the source of monochromatic light which we use, that will be already known. Maybe it is a sodium vapor lamp or a mercury lamp, and if we know what kind of lamp we are using, its wavelength will be available. So lambda value also will be knowing. L value can also be known with the help of the traveling microscope. Place the crosswire of the microscope at this end, then move the traveling microscope to this end. Just subtract those two positions, you will get the value of L. So L is also measurable with the help of the microscope, and by utilizing this value you can find the value of the diameter of the thin wire that is placed in the air wedge. So the diameter will be lambda L by 2 mu So this is about the interference by wedge shaped film. So please keep in mind the pattern will be equally spaced series of dark and bright fringes. And how can you even say that that will be equally spaced? Just look at this expression. The fringe width is lambda by 2 theta. This theta is the angle between the two glass plates, which will be constant. Lambda is the wavelength of the light source which we are using, that will also be constant, so that beta will be constant. So the fringe width which is available over here is constant because there are no varying terms in this expression. So beta value is constant, so we will get series of dark and bright fringes which are equally spaced, and this is all about interference by air wedge. Thank you.